Thank you everyone for participating. It's always interesting to see how challenges vary across plants, but typically we find that issues around forecasting, manual decision making, and maximizing gas utilization are common themes across the industry. As we go through today's session, we'll discuss how leading steel producers are addressing these challenges through digitalization. With that, let's get started. A quick introduction before we begin. I'm Kanksha Khandelwal, working as a digital solution consultant for sustainability at ABB. Joining me is Tarun Mathur. He is the global digital lead for metals at ABB. Now, before we move into the presentation, we'd like to hear directly from someone who deals with these challenges on a day-to-day basis. We're pleased to share a short message from Mr. Pradeep Agrawal, Head of Energy Management at JSW Dolvi, one of India's leading integrated steel plants. In his message, Mr. Agrawal shares his perspective on why effective management of byproduct gases has become increasingly important for steel producers, the challenges involved in balancing energy, cost, and sustainability objectives, and how digitalization is helping plants improve efficiency and decision making. Let's hear his thoughts.
Good morning everyone, myself Pradeep Wal. I am heading the energy management of India's second largest integrated steel plant with lowest CO2 emission and India's best energy efficient unit recently awarded by President of India. The steel industry is energy intensive and with carbon targets tightening day by day. To reduce energy and carbon emissions is matter of survival. Today I will talk about three things: why gas network automation matters, and how digitalization is driving efficiency, sustainability, and how JSW is leading the change. In an integrated steel plant, 40 to 50% of the energy comes from the gases. Blast furnace gas, coke oven gas, LD gas, and other gases which are low calorific value gases and fluctuating in generation and also on the consumption, and often wasted as flaring. Optimization the gas network means matching real-time generation with demand across boilers, power plants, and other furnaces like sinter pellet heating furnaces. Even 2% of the reduction in flaring saves crores annually and cuts CO2 emission. In case of Dolby, even 1% of flaring reduction is a 4 CR annually. It's about getting every kcal to be productive and not burning for nothing. Green steel starts with manufacturing intelligence, and in steel industry has to embrace technology in new way. It starts with MIS, data analysis, AIML, and tomorrow something else like digital twins, dark factory, etc. There is This is where digital transformation changes the game. With AI-based gas predictors, digital twins of gas network, and real-time calorific value sensors, we can forecast and surplus deficit 30-60% minute in advance. Advanced process control adjust mixers, pressure regulators, and booster RPM automatically. Results: higher gas utilization, stable furnace heating, lower gas fuel purchase, and reduced emissions. Digitalization doesn't replace people; it gives operation foresight. JSW is proving this on ground. We are deploying AI in every individual working, planning, shop floor, running furnaces, procurement of raw material, quality, logistic, even delivery of client. Because every role you have opportunity to improve efficiency and reduce energy. Roughly through AI we can reduce energy by 6 to 8%. AI is a fantastic technical solution because faster to adopt, low cost, insight to precision, and enables circular economy also. We are deploying integrated gas management system across Dolvi and Vijayanagar using AI and IoT to cut flaring by double digits. JSW was among the first to use advanced optimization for LD gas recovery and blast furnace gas distribution. They are also piloting digital twins for energy flows and investing in Industry 4.0 platforms. The tech-first mindset is why JSW consistently ranks among the most energy-efficient steel producers globally. Gas optimization is the low-hanging fruit for energy saving. Digital tools turns that fruit into an harvest. And companies like JSW shows that when we combine steel with software, we can get both profit and planet. The future of steel is smart, lean, and green. Thank you.
Well, thank you, Mr. Agarwal, for sharing those insights. And thanks, Kanksha, for the introduction. I think Mr. Agarwal's comments reinforce a key point that many steel producers are experiencing today. And byproduct gases are no longer just an operational consideration. They are strategic energy resource, and extracting maximum value from these gases requires greater visibility, better forecasting, and faster decision making. And with that context, let's look at the broader industry landscape and why gas network optimization is becoming a priority across the steel sector. So the steel sector is under tremendous cost pressure today. On the one hand, there is increasing pressure to reduce emissions and comply with evolving ESG and sustainability requirements. On the other hand, plants are expected to remain competitive while managing rising energy cost and operational complexity. In fact, 37% of organizations report challenges in keeping up with the ESG requirements. 34% indicate that reliable data remains a major challenge. And despite ongoing decarbonization efforts, around 70% of global steel production still comes from BF-BF route. And this is important because BF-BF plants generate significant quantities of byproduct gases such as BFG, COG, and LDG. And they are valuable energy resources. And in an integrated steel plant, up to 40% of energy demand can be supplied through these internally generated gases. And the challenge is utilizing them optimally while maintaining operational stability. And that is exactly where gas network optimization becomes relevant. So in an integrated steel plant, byproduct gases are generated as a natural outcome of the core processes, as you see on the picture here on the left side, where blast furnace produces blast furnace gas, coke oven produces coke oven gas, basic oxygen furnace produces LD gas, and so on. And these gases are generated continuously whenever the plant is running. And these gases are generally distributed through a gas network. And a typical gas network includes gas holders for storage and buffering, pipelines, mixing stations, compressors, boosters to maintain pressure. And then on the consumer side, as you see on the screen, on the right side, you have all these steel processes like reheating furnaces, it can be boilers, captive power plants. So essentially, it's a complex interconnected energy distribution inside the steel plant itself. And the objective is simple: utilize as much internally generated gas as possible and minimize dependence on the purchased fuels and electricity. However, gas generation and consumption are constantly changing based on process conditions and the periodic events that happen during the processes. And this makes balancing the network a highly dynamic problem. And that brings us to the value leakage that exists in most plants today. So at the core, all value loss comes from one issue: imbalance between the gas generation and consumption. And this can happen in a couple of ways. One way is, or one case is the excess supply, when the generation exceeds the demand and the gas holder levels rise, pressure increases in the network, and eventually gas has to be flared. And this leads to direct loss of the useful energy, and it has to be replaced by the purchased fuel. And it results in higher emissions as well. Case two, when there is a shortage of the gas, so when the gas supply is insufficient, the plant switch to natural gas LPG, and this results in higher and volatile energy cost or suboptimal fuel mix. And importantly, this can happen even in plants that flare gas at certain times, and on the other side, they have to use the purchased fuels as well. On top of this, decisions are mostly manual based on operator experience and limited visibility across the network, which leads to delayed response, conservative decisions, and suboptimal gas allocation. So overall, the value is lost by flaring through excess gas scenarios or the fuel purchase during shortage and inefficient decision making in between. So let's have a look at some of the real world scenarios, how it happens in real time. Scenario one explains when a blast furnace gas holder is approaching its upper limit, when the network pressure is rising and multiple captive power plants are available. And traditionally, operators react after the problem becomes visible. So they take action after these become available in the process parameters. So, but with forecasting and optimization, the system can predict excess gas availability in advance and recommend the optimal destination or distribution for the gases before flaring. Scenario two is similar, but due to stub changeover, which is a periodic phenomena in a blast furnace, and the gas demand changes suddenly, that affects the network pressure and the gas mixing station settings. And instead of waiting for disturbances to happen, such a software or the gas network optimization system forecasts the impact in advance and recommends the new optimal operating point. Scenario three is on the other side, on the demand side, when an unexpected process interruption occurs. For example, a reheating furnace suddenly reduces consumption due to various reasons, and the gas demand drops immediately. Again, the system forecasts the resulting imbalance and identifies the best utilization strategy for the excess gas. So these examples may appear simple, but when hundreds of such events occur across a plant every day, optimization becomes extremely difficult without digital assistance. So how do we turn these complex decisions into actionable recommendations? So for that, I'll hand over to my colleague Kanksha, who will walk us through the ABB's approach to gas network optimization.
Thank you, Tarun. Um, the scenarios we just discussed highlight a common challenge across integrated steel plants, right? The gas generation and consumption are continuously changing, and operators need to balance multiple variables in real time. So the real question is, how do we move from reacting to events to anticipating and optimizing them ahead of time? So for that, first we need visibility. We must understand what is happening across the network. Uh, Second, we need forecasting. We must anticipate future gas generation, demand, and network conditions. And third, we need optimization. We need a system that continuously determines the best allocation strategy, considering all operational and economic constraints. So let's briefly see how each of these modules contributes to solving the problem that we just discussed. ABB Ability EMS delivers gas network optimization through three closely connected modules. Let's start with monitoring and reporting. This module creates a single source of truth for the gas network. It continuously tracks the gas generation, the gas consumption, network pressures, CPP performance. Now, this provides the operators with the complete visibility into what's happening across the network and eliminates the need to rely on multiple disconnected systems. But monitoring alone is not enough, right? It still remains reactive in nature. So that brings us to the second module, which is forecasting. This uses AI ML, and the system learns from the historical operating patterns and continuously predicts the gas generation, gas demand, and potential excess or shortage kind of situations that Tarun just mentioned. This allows the plants to move from reactive management to proactive planning. The third module is optimization. This module transforms forecasts into actionable recommendations. So it continuously evaluates different operating scenarios and determines where the excess gas should be sent or which CPP should consume the gas, whether the gas should be stored or utilized immediately, etc. And this is also where Gen AI can further support operators. Alongside the the optimization recommendations, ABB EMS Copilot enables the users to interact with the system using natural language. For an example, an operator can ask, show me similar situations from the past month, right? And the Copilot can quickly retrieve historical operating data, trends, and supporting context, helping the operators understand and validate those optimization recommendations with greater confidence. So rather than simply providing an answer, the system provides both a recommendation and the operational insight behind it. So in summary, the monitoring is telling us what is happening, forecasting tells us what is likely to happen, and optimization tells us what should be done about it. So once these modules are in place, the impact is very tangible. In fact, if you recall Mr. Agrawal's message at the beginning of the session, he emphasized that effective management of byproduct gases is not only an energy challenge, but also an operational and business challenge. And that's exactly where the value of GNO comes from. Let's look at the benefits across 4 dimensions, right? Starting with the financial impact. Every cubic meter of gas that is recovered and utilized effectively is a cubic meter that doesn't have to be replaced with purchased fuel or electricity. So the plants can reduce the dependence on external energy sources. They can better utilize the excess gases and reduce the costs associated with process disruptions and energy imbalances. So in simple terms, the plant can extract more value from assets and energy resources it already has. The second area is operations. The gas management decisions involve multiple stakeholders, from the EMD or the energy management department and the captive power plants to the production units, right? A common challenge is that everyone sees only a part of the picture. So by creating a shared view of the network and providing forward-looking recommendations, EMS improves this collaboration, supports better planning, and helps teams to prepare for abnormal situations before they become operational problems. The third area is sustainability. Reducing flaring directly translates into lower emissions and better utilization of internally generated energy. At the same time, it supports regulatory compliance and aligns with the broader decarbonization and ESG objectives that many steel producers are actively pursuing today. And finally comes safety, right? For example, the stable gas holder levels and network pressures are critical for safe operations. By anticipating the imbalances and recommending corrective actions early, the system helps reduce the risk of gas accumulation or pressure excursions and emergency interventions. It also reduces operator stress by providing greater visibility and decision support. Now, to make this more concrete, let's look at a real-world example where these principles have been applied. This reference comes from the Fos-sur-Mer steel plant in France, one of the largest industrial sites in the country, with an annual steel production capacity of approximately 4.5 MTPA. Like many integrated BF-BOF steel plants, the site operates a complex energy ecosystem that involves the blast furnace gas, coke oven gas, LD gas, captive power generation, multiple energy consumers across the plant. And managing this network is challenging because the gas generation, power demand, and the energy prices are constantly changing. They are exposed to the open energy market there. The objective at the site was not simply to reduce the flaring. It was to continuously determine the most economical use of available byproduct gases while balancing the gas holder levels, CPP operation, the electricity market conditions, its own internal energy demand, and the fuel substitution opportunities. So ABB implemented EMS that continuously evaluated these variables and supported the gas dispatching decisions in real time. As a result, the site achieved approximately 10% reduction in the gas flaring, meaning more byproduct gas was converted into useful energy rather than getting wasted. Around 15% improvement in electricity procurement, forecasting accuracy for that. And of course, that led to the plants making better energy purchasing decisions. and an average saving of approximately 15k euros per month through improved utilization of the available energy resources. This is more than a decade back. So at this point, let's take a look at the EMS solution in action.
Every industry needs to use energy and water more sustainably. Yet no two businesses use them the same way. ABB Industrial Software for Sustainability has built-in processes for working towards carbon neutrality. By showing you the real financial and environmental impact of your operations, you can set realistic targets, reduce risks, and achieve more. Whether that's making significant greenhouse gas reduction and increasing annual energy performance in cement production, predicting deviations from energy contracts, emission limits, and better planning, shifting your paper production to times when energy is cheaper, or digitally orchestrating complex distribution networks. From your steel business for electricity, steam, and byproduct gases. Whatever the challenge, our purpose-built, industry-specific software is customized to make you more competitive. And the very same digital infrastructure forms the foundation for your cybersecurity and future improvements. So you meet and exceed your goals year after year. ABB Industrial Software for Sustainability. Solutions that revolve around you.
Okay, so that brings us to the end of today's session. To summarize, byproduct gases remain one of the most valuable energy resources in the integrated steel plants. Gas network balancing is becoming increasingly complex. The manual decision making is no longer sufficient for that. AI-enabled monitoring, forecasting, and optimization can significantly improve gas utilization while reducing flaring costs and emissions. Thank you for your time and participation. We would now be happy to take your questions.